This is a machine that crushes the quartz so that the gold can be extracted. Now, the one that's available for the tourists to see is very large, but it's difficult to see the insides to see how it's working. Now, this machine is 3 stories high, and I was able to get up the stairs all the way to the top level, but tourists aren't allowed up here because it's obviously dangerous, and that's why I built a model to show how it works. This camshaft weighs 3 tons, so it was quite a job to get it lifted up there, and every one of these hammers weighs half a ton, and they're dropping about 9 inches onto the quartz and crushing it. At the peak of production, there were almost 900 heads of actual stamper heads in production, and they would all be running at the same time. So you can imagine the tremendous noise that was produced. This is in the middle of a housing area, so they only run it for about 90 seconds or so at a time, maybe a bit longer. And this is a view that the tourists get. So a lot of it's covered in timber, and you can't actually see the cams from this level. You can see the water coming through the screen and over the tables. On one of the stems you see a thing that looks a bit like a top hat going up and down. That's operating the ore feeder. Quartz rock is extracted from the mine up in the hills behind the stamper battery, and gravity is used to assist them in transporting it, and crushed to the size of golf balls by a jaw crusher and fed through a hopper into the back of the stamper. This machine is known as a Wilfley table, and it works rather like a gold panning pan. Water and fine sandy material flowing over it gets caught on the little rails, and the heavier gold settles in, it catches behind the rails, and the lighter materials get washed off. The lighter materials are processed further. They go through a ball mill, and then the burdan, and this is a burdan. It's like a dish. The original ones had a cannonball in them that rolled around the side to crush the quartz, but this one has a steel slug which just drags across the surface. In the burdan they'd often put about a litre of mercury in the bottom, and that would amalgamate with the gold. There's the ball mill. It would be filled with steel balls a couple of inches around, or otherwise pieces of flint. This is my model stamper battery. The frame is aluminium, the cams and flywheel are brass along with the shaft. The lifters and hammers are all stainless steel. In front of the device we can see a copper plate. The original ones were actually made of Muntz metal, which is a kind of brass, 70% copper and 30% almost of zinc and a tiny bit of iron. This metal was used because you could spread mercury on it and it would stick to the surface. As the gold powder came across that surface, the gold would stick to the mercury and form an amalgam. Once a sufficient amount of gold had accumulated there, they would scrape it off and put the amalgam of mercury and gold in a retort and boil off the mercury. And this left behind the gold bullion, which is a mixture of gold and silver. The percentage of gold varies depending on the location where it was mined. In these close-ups you can see the tappets and the cams that lift them, and lower down we have the hammerheads with their removable shoes and anvils. And the shoes and anvils would wear out in about 3 months and they had to replace them, so they are removable. Now perhaps it sounds a little more realistic in slow motion. If you look closely, you'll see that the cam rubbing on one side of the cam follower causes it to rotate. It makes the whole shaft and hammer rotate. Now the screen or coarse filter is removed. When we use it to crush some quartz, you'll see that it's actually rotating and grinding as it hits. And is actually causing the anvil in the model to unscrew. It's just held in with a screw from the bottom. There was some debate at the time as to whether there was a grinding effect, and I think it clearly is. This is an unusual mechanism which drove the ore feeder. It's a kind of brake or clutch mechanism. Brake shoes sitting on the rim of this wheel will catch when it's at the bottom, sling the lever upwards, but when they got to about horizontal level, it would lose contact and would drop back down again, and then grip again. So it would do a repetitive motion. I used a different design in my model stamper battery. I used a ratchet system, which turns the disc a little bit each time. And as it turns around, there's actually a wiper blade that should be on top of the disc, which causes the stones to get wiped off into the back of the mortar box, and this just turns around very slowly, driven by one of the stampers. Now, if that stamper is already full of rocks, the stamper can't actually drop all the way, the ratchet doesn't work, and therefore more rocks don't get fed in if it's already full. Now, to make this model, one of the key problems was to make the cams. And that's something I thought about for a long time, is how to make a cam shape like this on a lathe. And as you can see, there are a variety of different cam designs around, depending on the height of the lift, the weight of the stamps, and the speed that it's going to operate at. The speed is quite critical, actually. It takes a certain amount of time for the hammer to drop regardless of how fast the cam is going around. If you turn the cam too fast, it'll come down and hit the cam before it's finished the rotation and do some damage. This particular drawing of a cam shows a fairly steep curve on the cam with a large gap between the two arms of the cam. So there's more time for the cam follower and hammer to drop before it hits the next cam and starts lifting again. And that means the machine can be run faster. It was also found that if you decrease the height of the drop, it would decrease the amount of time that the hammer took to fall. And to compensate for the decreased impact, you would increase the weight of the hammer. And then you could run the machine faster and get more efficient results. The shape of the curve is known as an involute curve, or otherwise as Archimedes' spiral, because it was discovered by Archimedes 300 BC. When the cam is rotating at a constant speed, it results in the cam lifter rising at a constant rate and putting an even load on the steam engine. Actually, the majority of stamper batteries were run on water wheels, and some later on Pelton wheels, but when summer came and it got very dry, they'd run out of water and would have to resort to steam and using coal. Just as you drive into the town of Thames, you see a welcome sign, and there is a stamper battery erected there. And you can see on that battery some damage which has been done by this camming effect with broken parts and bruising of the cams. There's even a broken cam follower or tappet, and you can see this has been turned upside down so they could use the other end. They are designed that way so that they can be flipped over when they're worn. This tappet is held in place with tapered wedges which push a plate or gib against the stem. This cam has an angle across the end to allow the cam follower to drop off more easily. On this hammer you can see that both the shoe and the anvil are quite worn, but worn evenly because of the rotation.